So, good morning, everybody. I'm Ali Tajer, Associate Professor with ECSE. I'm a member of the Information Sciences and Systems Group. That's a group that encompasses research areas on communication and networking. Professor Abu Zaid, Professor Carr, and Professor Malik, who talked, includes computer vision and image processing, which includes Professor Chang Ji, who just talked, Professor Radke, and Professor Yazici, as well as signal processing and machine learning, includes Professor Chen, who I believe you'll be talking later, Professor Mang Wang, and myself. I also work on communication systems as well. So what I'll do is I'll very briefly provide an overview on a broad perspective of the projects that I work on. And I believe a number of you will be talking to me later. I'll be happy to go over the details when we talk. So my research is more on the analytical side of a number of domains, but all of them are driven by a number of applications. So mainly problems in wireless communications. And more specifically, I'm interested in larger scale systems in which we have to make decisions about the resource allocation, optimization in a distributed way. So that is opposed to traditional communication systems in which we generally work with toy examples, small problems in which we have real, idealistic assumptions about what we know about the network. We want to relax those assumptions, see if we have a very large scale network with very with radios that are low budget, what we can do for allocating resources. So one driving application of that is, for instance, the Internet of Things. Another aspect of it is how we can look into the latency or the delay in such networks. So specifically driven by applications such as mission critical services, for instance, let's say remote surgery, reducing the latency in communication systems is extremely important. You want to have a near real-time communication between the transmitter, that could be a surgeon, and the receiver, which could be a robot doing the surgery on a patient. So that is one domain. The second domain is learning and inference, especially over networks, and I'll get into the details of that in a moment. And the third domain, which is on the more application side, is the power system. And we look into problems like detecting anomalies, cascading failures, forecasting electricity market, and so forth. So in most of them, there's always a notion of optimization or statistical inference. All right, so what I'll do is I'll just focus on learning and inference problems over networks. I'll go over one specific problem that could put some perspective about the domain that we work on. So that is a domain which is known as active learning. So in active learning, always there is the question of how to collect data in an intelligent way such that it caters to the purpose of the decision maker or the machine that eventually wants to make a decision about the objective that you have. So if you think about a machine learning pipeline, it usually has three main components. One is the data acquisition part, data collection part. The second part is data processing, and the third part is decision making. Now, often these three components are designed in isolation. So design and optimize in isolation for good reasons, because each of them is super complicated. So what we are trying to do here is to see if we can have a design for each of the components that is at least partly cognizant of what happens in the other two components. So for instance, let's assume that we want to design a classifier. So red dots and green dots, there are two classes. Let's say that you want to make a medical diagnosis tool that wants to classify people into patient or healthy. And you want to have a classifier, which is the line that could put the border between the two regions, healthy and sick regions. Now, always one question, especially let's say in medical domain, is that how many data points do you really need to properly train your machine so that it can perform classification properly. So that is one example of saying that by keeping the objective in mind, which is ultimate classification, how we can design the data acquisition part, which is the collection of samples or the data from the patients. So one big question that arises in all of this is that how much training data is necessary or sufficient for a specific training perspective, objective. So that leads us to the question of learning-driven data acquisition. So if I go back to that machine learning pipeline taxonomy that I mentioned, so the ultimate or the last stage of that process was decision-making. And we want to see what decision-making objective we usually have so that we could leverage that properly in order to design the data acquisition aspect of the problem. So that area is broadly called active learning. And we look at the problems in that domain from both machine learning and statistical learning perspectives, especially when we have a notion of network in the data. So what do we mean by network? Let's start with a very basic example. I'll mention what it means in reality, in practice, this example. Let's say that you have a bunch of data points, x1 to xp. But these data points are somehow interrelated. They're not independent of each other. This is essentially the graphical model that Professor G was just talking about. Now, by looking at the data, we want to infer how these data points are related with each other. So that relationship is captured by the edges that are connecting the nodes. So the thicker the edges, it means that the more interconnected or more coupled to vertices in this graph are. Now, by looking at that data, we want to infer the graph, and that is the problem that we call a structure learning, learning the structure or the connectivity of a graph. Why is it important? Appears in a wide range of domains. A couple of them we are working with IBM and a medical school in Toronto on brain modeling, for instance. So essentially, we are looking at brain images, and in order to detect concussion, or more specifically, early the symptoms of concussion. So we know that concussion, when it happens, its effect will be changing the behavior of the interactions that the neurons have in the brain. So those change of behaviors would be a good signature for detecting concussion. Another example is learning the genetic networks. So we know that, for instance, if you look at different subtypes of a certain cancer, for a subtype, you could find the genetic network. And always the question becomes is that, if you know that structure, how can you leverage that in order to learn the structure of other subtypes of the same cancer? So that is important because you know that being the subtypes of the same cancer, they share a level of genetic network, but also being different subtypes, they have their own independent structures as well. So that brings us to the notion of learning multiple graphs at the same time. That is what we call joint structure learning, or learning the shared clusters in graphical models. Yes.
We have like another 30 seconds. How about that?
All right, that's perfect. So very briefly, on the wireless domain, I work on three aspects: on data storage, data communication, and data computing. Data communication is perhaps the core part of my work. Data computing is something that I recently started working on, and that is mostly in collaboration with Professor Melek, who described this in more details. And data storage, as they pertain to data compression, is another domain that I work on. All right, that's it.
Thank you, Ali.